Hello, everyone. This is Lab 4 for Physics 2212, Faraday's Law, and this is our fourth and final lab. So, this lab, the purpose focuses on magnetic induction and eddy currents. Specifically, we observed what happens when a bar magnet falls through an aluminum tube and compared that to the real world behavior to a computational simulation built in GlowScript. Our system consists of the magnet and the aluminum tube, and everything else will be treated as the surroundings. Um, and we have a quick little preview of our results where the measured time was about 1.3 seconds, and the simulated fall time was about 0.912 seconds. And so here are some key principles to understand. To understand what's happening, we use four major concepts. Faraday's law, a changing magnetic field induces an EMF in a loop, described by this formula on the right. The Biot-Savart law, a steady current creates a magnetic field whose strength can be calculated using the equation on the right as well. And then Newton's law, especially the second and third, where net force is related to acceleration, and every action has an equal and opposite reaction. And then we have Ohm's law, V equals IR. So in the actual experiment, I dropped the bar magnet down an aluminum tube and measured the time it took to exit. Here is a visual demonstration I have put on the left, and so there is a upward magnetic force created by induced currents in the tube, and this force opposes gravity and slows the magnet's descent. To simplify the analysis, I also made a few assumptions, neglecting air resistance, modeled the magnet as a magnetic dipole, and consider only magnetic and gravitational forces. Um, Here are all the measurements on the right, and the trial average time ended up being around 1.327 seconds. And in the glow script, I started by defining initial conditions, magnet and two properties and physical constants. And then I calculated the magnetic field and flux of the core of the code involved used the defining forces of upward magnetic force and downward gravitational force. The net force was then used to update the magnet's velocity and position over time. Here's a deeper look into the computational model I made on GlowScript as well. And so here we are with the data and visualization results. So from the graph, we see something pretty interesting. As the magnet entered and exit the tube, the gravity dominates and it accelerates. But in the middle of the section, magnetic and gravitational forces balance out, resulting in a constant velocity, surprisingly. And this behavior aligns with the theory and confirms our prior knowledge and concepts. And so I also wanted to have some questions I wanted to consider, like how do real world and simulated fall times compare? So if you remember, the simulated time was actually slightly faster, most likely due to the neglected air resistance and human timing errors. And I also wanted to show that um, the graph shape show that forces are unbalanced at the ends, but balanced in the middle. And then here are some potential errors and what ifs. So some potential sources of errors, like I mentioned before, is air resistance, as it may have slowed the magnet despite being considered negligible. Magnet wall contact, so friction or collisions if the magnet touches the inner tube of the wall. Um, Timing inaccuracies, human or in device related measurements may have been inaccurate, and that could have led to inaccurate data. And so, what if the tube had near zero resistivity? Ohm's law tells us that induced currents would increase. This would generate a stronger magnetic field and slow the magnet even more. And then if we added holes to the tube, fewer induced currents would form, weakening the opposing field and causing the magnet to fall faster. And that is it for Lab 4.